Okay, here's an example. So we're going to apply the theorem to this example. So we've got a function, so we've got a sequence that's defined by this function here, okay, and in terms of n, right? So we know that this here represents a sequence, right? A sub n, right? So this would be 3 over n squared. We know how this behaves. We know that the limit, right, converges. So we know that the sequence, so let's do this. Let a sub n equal 3 over n squared. And we know that the sequence a sub n converges to 0. We also know that cosine is continuous at 0. So using the theorem, we know that, again, the sequence of f of a sub n converges to f of L, which is 0 in this case. Well, what's the function? The function is a cosine function. So if we put this all together, we know that the limit as n approaches infinity of cosine 3 over n squared is equal to cosine of 0, which equals 1. So in other words, because this is a continuous function and we know the behavior of the sequence here, we can literally take the cosine, in other words, of the limit as n approaches infinity of 3 over n squared, right? And this limit goes to 0, right? And we get the result. Okay? So the theorem allows us to be able to know based on the conditions, right? So we've got a convergent sequence inside a function. And we know that that sequence converges to a number. And so, and the function is continuous at that number, at that limit. So therefore, we know that the limit of the sequence, we know the sequence of this, right? Right? F of a sub n, this sequence converges to f of L, which is f of 0. And so in this case, it's 1. And we're done. It's that easy. So the theorem allows us to be able to figure out whether it's convergent or divergent easily. So let's do another one.